Okay, I think it's three. I think we can start. So good afternoon and good morning, depending where you are. Thank you for joining us to this webinar. Today it's a pleasure to introduce Mingyu Kang. We met recently at SAQuTI in Seoul, at the Asian Quantum Information Science Conference. And checked it, and I thought that would be a very nice idea to invite him to give us a talk in this work. Yeah. Mingyu is a PhD student at Duke University, working with Professor Kenneth Brown, and he works on theoretical aspects of quantum control, error correction, simulation. And today he will speak about his experience on simulating chemical things on ion-based quantum computers. Yeah. So Mingyu, thank you very much. You're welcome to start. We set up this webinar as a meeting in Zoom technical speak, so that people can ask questions if you are happy with it at any time. Yeah.
Yes.
Without many formalities. Yeah. So please, you're welcome to start. Yeah.
Yeah. Thank you so much for inviting. Please feel free to interrupt anytime. So, yeah, this is a review paper we wrote with Professor David Berton and Ken Brown's group. And as we all know, chemistry is a very complicated open quantum system. And as you can see from the thickness of this book, it's a open quantum system is a hard problem. So we hope to solve this chemical dynamics problem that cannot be solved using classical digital computers using trapped ions. It's a far-fetched goal, but we want to go to that path. And I hope you enjoy this talk. So analog quantum simulations have been arguably used already for practical purposes, like solving problems in physics and material science. You can look at this very nice perspective paper. And also, of course, there has been a lot of exciting experimental works in platforms such as optical lattices, Rydberg atoms, and superconducting qubits. And the common theme of these papers is that they are looking at many-body dynamics of a system in a scale of about 100 qubits. And as you all know, the exponentially large Hilbert space size makes it classically challenging to simulate these many-body dynamics. So then you can ask, if you're already performing analog quantum simulations of this size, can we say we have already achieved quantum advantage? And the answer to this question is not a simple yes or no, because you really have to analyze the trade-offs, complicated trade-offs of all these factors, such as system size, accuracy, the level of approximation, structure of the Hamiltonian, and the computational cost. So for example, let's say your analog quantum simulation was able to simulate a 200 qubit system with some accuracy. It sounds challenging for classical computers, but you may still be able to find the classical algorithm that employs a more relaxed approximation or sacrifice some accuracy so that you can run that algorithm with a reasonable runtime. So because you have this trade-off, suggesting a definitive quantum advantage is a very challenging problem. Nonetheless, we want to go in this direction. So and the problem we want to solve is chemical dynamics. And the reason is it's a very interesting quantum problem. So the diagram here visualizes the FMO complex, which is a protein complex that is known to have important roles in photosynthesis. So what happens is this donor state can be excited, and then this excitation gets transferred through all of these bridge electronic states, and then it arrives at the acceptor state. So the energy is transferred from here to here, and the high rate of energy transfer in photosynthetic systems, high energy transfer efficiency, has long been a very interesting subject of research in biology and chemistry. So people have been thinking whether quantum effects have a role in photosynthesis. So in 2007, it was suggested that the quantum coherence of these electronic states may play a role in photosynthesis. However, this was quickly refuted by many groups, and now it is generally believed that only the electronic states quantum coherence may not have a role, simply because the dissipation of the electronic states is much faster than the energy transfer. However, now it has been suggested that vibronic coherence may play a role in photosynthesis. Here, vibronic means vibrational plus electronic. So because all of these nuclei of these sites may have some vibrations, and you can consider it, model it as quantum oscillators. So if you include those quantum oscillators into your quantum system and consider the coherence of the larger system of combined electronic states and these quantum oscillators that represent the vibrations, then the coherence of the larger system can probably explain photosynthesis better. And also, a very interesting recent work showed that even a single photon can induce the entire photosynthetic process experimentally. So yeah, I hope all of this convince you that energy or electron transfer in molecular systems is a quite interesting quantum phenomenon. So we would like to understand it better using trapped ions. And the model we want to look at is the so-called linear vibronic coupling model. So here you have electronic states and vibrational modes, and your electronic states can be coupled to each other, and also your electronic states can be coupled to the vibrational modes linearly. So this kappa is the vibronic coupling strength. And this model is general in a sense that any electronic state can couple to any other electronic state and also to any vibrational mode. So we think this model can describe a large class of chemical models, such as photosynthetic energy transfer and protein electron transfer, and so on. And again, we want to simulate this using trapped ions. So this is what the trapped ion system looks like. This is a chip from IonQ. The chip size is a few centimeters. And if you zoom into this ion trapping zone here, you can see that the ions are trapped with 5 microns apart from each of the nearest neighbor ions. And you can use lasers to illuminate these ions and do operations on the ion qubits. So the next slide is my attempt to explain trapped ion physics in a single slide. So first we have to choose, define the trapped ion qubit. We do that by choosing 2 atomic states of the trapped ion. In our case, we use the hyperfine states because they are stable and very accessible using lasers. So you have the 0 and 1 state of a trapped ion qubit, and to do operations using lasers, you use this 2-photon Raman transition that uses an excited atomic state as a bridge. And you can define the drive frequency of these lasers by the frequency difference between the global laser beam, the global laser beam, and the individually addressed laser beams, minus the qubit frequency. So it's the frequency difference of the lasers minus the qubit frequency is defined as the drive frequency mu here. And of course, the way how you trap the ions is you use this radio frequency electromagnetic trap. So we all learned from electromagnetism course that a static electric potential cannot trap a charge, but if you oscillate it with a radio frequency, you can. So this confinement force from the trapping potential and the Coulomb repulsion between the ions balance out and create these what we call the motional modes, which is simply the normal modes of the collective motion of the ion chain. So, for example, you may have this center of mass mode where the ions move in the same phase, and also other modes where represented by other normal modes. So n ion chain will have 3n motional modes, n for each of the directions. And most importantly, each motional mode can be represented by a quantum harmonic oscillator. So if you have an n-ion chain, you not only have n qubits, but you also have 3n harmonic oscillators. And we can use them for chemical dynamic simulations, as you will see later. So let's see what the basic operations we can use are. So first, if your mu is 0, which means that your lasers are just resonant with your qubit frequency, then you can apply standard single qubit gates. And if your mu is nearly resonant with your motional mode frequency, so note that you have a blue sideband and a red sideband applied together, then you can apply what's called the spin-dependent force. So to see what happens here is you can go to the phase space of the state of this quantum harmonic oscillator, and your state is displaced, but displaced to a different direction depending on your qubit state. That's why we call this a spin-dependent force. So you have that. And if you apply spin-dependent force on 2 qubits simultaneously, and you do that carefully so that your motional modes are displaced during the operation, but somehow come back to the origin at the end of the operation, then what you can do is you can entangle the 2 qubit states. So you can do 2 qubit gates. And the area enclosed by this trajectory quantifies how strong your 2 qubits are entangled. But again, your motional mode should come back to the origin so that there's no residual entanglement between the qubit and the motional mode. And you're only left with the qubit-qubit entanglement. So these are the 3 standard operations that we use for trapped ions. And we want to use them for simulating the LBCM. You can look at this very nice paper as well that proposes this. What we will assume here is that we'll only work on the single excitation subspace, because fortunately that's what chemistry often does. And this allows us to not worry about all these like complicated like fermion exchange statistics and so on. So a simple mapping from the molecular state to a trapped ion state is possible. So for example, for an electronic state where only your ith state is occupied, this molecular state can be mapped to ith qubit in one state and all other qubits in 0 state. And your kth vibrational mode can be mapped to the kth motional mode of the trapped ions. And then for the most general purpose, you can just do trotterization, meaning each term in this molecular Hamiltonian can be directly mapped to trapped ion operation. So you simulate evolution with respect to each term one by one for a short time step, and you repeat for all the terms and all time steps so that you induce the evolution of the entire Hamiltonian. And a big advantage of trapped ion system is that basically we have an all-to-all connected device. Even if it's a linear chain of ions, you don't only have like nearest neighbor connections, you have all-to-all connections between the qubits. And also, since the normal modes are shared by all ions, you have all-to-all connections between the qubits and the modes as well. So this allows a very good flexibility in the structure of the molecular system that you want to simulate. So to be precise, this term can be simulated using either single qubit gates or 2 qubit gates. And this term can be simulated using the spin-dependent force or the combination of all 3. Okay, so that's the good news. We can simulate LBCM using trapped ions. But of course, the drawback of analog quantum simulations is that you have a noisy device. For example, our biggest source of noise is the voltage that goes into the trap electrodes. And of course, these voltages determine the trap potential and therefore the motional mode frequencies. So you see all these small oscillations in the trapped electrode voltages, and that makes your motion mode frequencies fluctuate over time. And that's what we call the motional dephasing, which is the biggest source of error in our system. And also you have motional heating due to all sorts of, like, for example, you have like stray charges in the chip, and yeah, you don't understand this phenomenon really well, but anyways, what happens is your phonon number increases over time. And you may also have laser dephasing, meaning your optical phase of the lasers may somehow fluctuate over time. So these are the three main sources of errors that we have in the system, which is bad news, but at least we understand the noise really well, which is really good for trapped ion systems. So just to advertise my another work, what we did here is we can measure the motional dephasing spectrum and filter it out using pulse optimization to do high fidelity 2-qubit gates. So you can see that the error budget due to the motional dephasing is significantly suppressed, and therefore your experimental gate error is also reduced. But the point I'm trying to make here is that the experimental error budget and the simulated error budget is pretty good. So we believe we understand the error budget really well. So we want to use this to see how well we can perform chemical dynamics simulations with trapped ions. So what we did in our review paper is we did a test match between analog trapped ion simulations and state-of-art classical digital simulations. So we choose a very simple toy model. This model will not give you quantum advantage because it's so simple. It's a donor acceptor system coupled to n vibrational modes with vibronic coupling kappa. And yeah, we know how to simulate this very well using classical computers, but we want to just do this test match. So we'll use this parameter reorganization energy, which is commonly used in chemistry, which is just proportional to kappa squared. And we will assume that the modes are high frequency so that the initial phonon number is negligibly small. And the classical algorithms we will compare against are, we choose two of them. First is the time density matrix denormalization group method, which is a numerically exact method. And the second method is the well-known Ehrenfest, which is basically a semi-classical approximation that is probably not the most accurate one, but is computationally very efficient. So we will compare the noisy trapped ion simulations with these two classical methods. So these are the test match results. So we have 4 curves, as you see here. And I would like to emphasize that none of this is experiment. These are like simulations of how the trapped ion system evolves. But we believe we can provide pretty good predictions of the trapped ion system. So first, the TDMRG and the ideal trapped ion simulation match really well, as they should. There's no noise, then it should follow the exact evolution. So we see the blue and red curves perfectly overlap. And let's look at the Ehrenfest curve. The Ehrenfest curve matched well with very short time scale, but then deviates because Ehrenfest, of course, cannot capture all the quantum coherence, quantum oscillations. And however, if you go to very large coupling strength like this, then it performs better in terms of capturing the overall energy transfer rate. And that is because in this regime, your oscillators are highly excited and therefore behaves classically. If your quantum oscillators are highly excited, then it's closer to a classical behavior. So keep that in mind. And then let's look at the important noisy trapped ion simulations, which assume basically the noise parameters of our trapped ion system. And you'll see that when your coupling strength is very small, not very small, we don't call this very small. It's like it depends on the literature. But anyways, when your coupling strength is small, then you only need a short experiment to simulate the entire evolution. So your noise doesn't come into the evolution too much. So you have a pretty good match with the ideal simulations. But of course, as your coupling strength grows, your pink curve starts to deviate. And when it's very large, then now it's like, yeah, your experiment time for each run is closer to the noise time scale. So you don't have a very good result. We were really interested in this match between noisy trap ion simulations and Ehrenfest over here, because this suggests that even noisy trap ion device may, if you have a controlled amount and type of noise, then this suggests that noisy trap ion simulations may simulate some intermediate regime between like quantum and semi-classical evolution. But of course, that has limits, and if you go to longer experiments, then the noisy trap ion simulations deviate from Ehrenfest as well. And one thing to mention here is that to get each of these data points for trapped ions, you have to run the evolution many times, because each run gives you only binary result, either 0 state or 1 state. So you have to repeat this R times. And because you only have a finite number of runs, you have this shot noise. This can be troublesome if you have, like, for example, like about 100 shots. But we don't think shot noise is like a fundamental problem for trap ion simulations, because shot noise is unbiased and completely independent for each run. So we believe that even with shot noise, we can get the overall rate of energy transfer, for example, pretty accurately. And now we can compare the runtime of the TDMRG method and trap ion method. First, let's look at TDMRG. As you increase the reorganization energy, you can see that it roughly increases exponentially with this ratio. And here we have two sets of curves. One is the solid and one is dashed, and that's for two different errors allowed. So all population errors are less than 10 to the minus 3 for the solid curves and 10 to the minus 2 for the dashed curves. And you see that you can do this trade-off between the accuracy and the runtime. And yeah, for the 10 to the minus 2 error, the rate of exponential increase is much more suppressed. But anyways, at least for high accuracy, we see a pretty clear exponential increase in the runtime. Meanwhile, for trapped ions, the estimated total simulation time is a sublinear in this ratio, or linear in kappa. And that's, of course, because your molecular interactions are directly mapped to the trapped ion operations, so it's, of course, linear. Oh, I forgot to mention, meanwhile, for the classical digital method, the entanglement between the molecular components is stronger for a stronger value of lambda, so that's why we expect this exponential behavior. And this dashed line is the time spent for the cooling, state preparation, and measurement. So that is included in this simulation time estimation. Yeah. Any questions so far, or are we good?
No, I think we're good.
Yeah, thank you. So this was a toy model. We already can run these TDMRG runtime. So this does not lead to quantum advantage, of course. We want to see what the state-of-art classical digital calculations can do. So we looked at these papers as examples, which simulates a very similar model, which is a homogeneous polymer of 20 electronic sites with only a nearest neighbor electronic coupling. And each electronic site is coupled to 2 harmonic oscillator each. So there are 40 total harmonic oscillators. And the important difference from LBCM is that each mode has additional dissipation to a thermal reservoir. And this will be explained briefly at the end of my talk. So but this will still give a rough sense of like how hard it is to simulate LBCMs. And they can simulate the population dynamics, as you see here. And here, the ratio of lambda to delta was about 1.25. Meanwhile, in the previous plot, we were mostly considering a much larger lambda over delta regime. So, and in this value of lambda over delta, and for simulations that achieve numerical convergence, they required 60 hours of computation on a pretty high performing classical processor. So that's why this led us to suggest that there are good models that are classically intractable, but perhaps suitable for future trapped ion systems. So for example, if you have a few tens of electronic states and Bath modes that are that have moderately strong coupling to Bath, for example, your lambda delta being 10, and also if you have complicated connectivity of couplings between the electronic states and Bath modes going beyond the nearest neighbor electronic couplings, so that you can represent more complicated molecular structures, then in this regime, your entanglement problem will be much more severe for classical digital methods. And we had this exponential scaling over lambda over delta. So we think this could be a good target for achieving quantum advantage. So to visualize, numerically exact methods are limited, and approximate methods can probably perform well for very large coupling and very small coupling. So there's a gap here. And our hope is that noisy analog trapped ion simulations can fill that gap. And of course, this boundary where noisy analog trapped ion simulations can give accurate results depend on your noise level. So you need better systems. So yeah, you need a careful analysis of classical digital computation cost. And analog quantum simulation would probably require about 2 orders of magnitude longer coherence time or smaller heating rate compared to the state of art. Yeah, with that, so this is a quite far-fetched goal. So in the meantime, we want to explore some small-scale models that does not give you quantum advantage, but nonetheless shows interesting quantum simulations of small molecular models. So I would like to review those what previous trapped ion experiments have done and how these can be extended. So our first small example is a phenomenon known as conical intersection. So it's a donor receptor system coupled to 2 harmonic oscillators, and of course you can assume they dissipate energy to a thermal reservoir, as I'll describe later. But yeah, in this model, if you draw the potential energy surfaces of the donor and acceptor states, then and if you have this potential energy surfaces cross like this, then very non-adiabatic behavior can happen. So these wave packets can interfere, do all sorts of things. So the standard approximations like Born-Oppenheimer approximations wouldn't perform well. So you really have to simulate this entire system, an entire electronic states plus modes. So yeah, if you have many of these conical intersection, it becomes a problem for classical methods. Yeah, so this model has been experimentally simulated on trapped ions. So it's a donor receptor coupled to 2 modes with no dissipation. This is from our lab. This is from the University of Sydney. What we showed is that in the phase space of the X and Z coordinates, sorry, 1 mode was coupled to Pauli X and 1 mode was coupled to Pauli Z. So if you look at the phase space of X and Z modes, you expect a geometric phase that depends on the trajectory of the wave packet. And these wave packets may have destructive interference like this, or constructive interference, of course. So this is the simulated result, and this is the experimental result. And this paper also showed how these phase space evolution can happen over time. So yeah, of course, you can consider more complicated models with more conic intersections and add dissipations to the modes to better represent actual molecular systems. And the second small example is vibrationally assisted energy transfer. So the idea is for certain values of vibrational mode frequencies, you can allow a faster energy transfer that was previously forbidden without the vibrational mode. So your mode can be coupled to donor state or the acceptor state, or even have a correlated or anti-correlated mode that couples to both donor and acceptor state. And it is known that if you have these correlated modes, it's a very non-adiabatic, so it adds a lot of cost to classical calculations. So this is the model we proposed, but just consider only the third mode here, the couple to the acceptor, and this model has been again experimentally simulated using trapped ions. In this pretty much the first paper in this direction, they showed that the acceptor population, depends on the vibrational mode frequency. And in this recent paper, they actually simulated the entire vibronic spectroscopy using the data from the time dynamics. So yeah, this is the time dynamics, and this is the vibronic spectrum generated by it. And you can see a pretty good match between the experiment and the theoretical vibronic spectroscopy of a small molecule. So yeah, this was done. And also another small example could be polarized light-induced electron transfer. So the difference from the previous model is that now the electron, not only the excitation of the electron can transfer, but the electron itself can tunnel from one side to another. So in this first stage, you have the ground state of the donor, and then depending on the polarization of the light, you may excite to either the first donor state or the second donor state, depending on X or Y polarization. And then after your donor is excited, your electron can transfer to the acceptor site. So this is the photoexcitation part, and this is the electron transfer part. And this molecular structure may have a similar phenomena. You may notice that there are no vibrational modes here, but you can, of course, add them to better represent actual systems. So this model has been simulated in our lab on a trapped ion Qtrit. I was involved in this work, led by Ka, a very, very nice experimentalist. And you can see that the theoretical and experimental dynamics for both the photoexcitation stage and the electron transfer stage match really well. So we're very excited about this accuracy. This is my favorite result. So if you tune the ratio of the two energies of the donor states, your acceptor population fluctuates, and the resolution here is pretty amazing. So you can even resolve like 0.5% of population. And this shows that analog quantum simulations are capable of pretty accurate simulations, despite this model yet being very small model. So yeah, this was a review of what has been done so far on trapped ions of chemical dynamic simulations. And however, these were all limited to the linear vibronic coupling model. And of course, we want to go beyond that to better describe actual molecular systems. So if you look at the actual 2D infrared spectroscopy of a molecular system, you don't have like a super sharp peak along the diagonal, but you have this spread. And that means that your vibrational modes are themselves subject to dissipation to a thermal reservoir. And you also have these additional peaks. And this is a signature of anharmonicity. So your oscillators are not harmonic, but your 0-1 level spacing can be larger than the 1-2 spacing. So to better accurately represent the molecular system, you have to take these dissipation and anharmonicity into account. So there are several ways to go beyond the LBCM. First, you can include the dissipation of the vibrational modes. And this is also often described as simply continuously distributed modes that follow, for example, Lorentzian spectral density. And second, you can consider higher order interactions between the electronic states and the bath modes. And you can consider anharmonic modes. And these two things are particularly interesting because we believe that linearly coupled harmonic oscillators are particularly well suited for semi-classical analysis. So if you go beyond that, your classical computation will struggle more. So it's probably a better target for quantum advantage. So let's see how all of these can be simulated using trapped ions. First, the dissipative vibrational modes can be simulated using, we can think of at least two methods. So first is laser cooling. So you have to trap ions of different species and apply cooling on one of the ions. And then your vibrational mode will dissipate energy. But as you know, the vibrational modes are shared by many ions. So you can actually interleave this cooling operation with the unitary evolution and simulate the vibronic dynamics where the vibrational modes are dissipative. The challenge of this method is you have to trap two different species of ions, and you need a lot of lasers to do that. And the second method, and of course these may describe like different regime of dissipation, but anyways, the second method is stochastic kick method, which is basically randomizing your amplitude, frequency, or phase of the lasers that do the siphon kick operation. And if you repeat that many times and average over the results, that will represent dissipative evolution. Okay. And the second one was the higher order interactions. And this was already demonstrated by all these very nice works. For example, you have a spin-dependent beam splitter Hamiltonian. You have two oscillators here. And a single Rabi cycle could be experimentally demonstrated. And of course, the challenge here is that your single Rabi cycle is already in the order of 1 millisecond. So to actively use these for accurate quantum simulations, you may need longer coherence time of your trapped ion system. And finally, the anharmonicity, more work has to be done. If anharmonicity is weak, then you can treat it as, for example, third order interactions, but a general way of treating this needs to be explored. So yeah, that pretty much concludes my presentation. So we hope that analog trapped ion simulations can provide advantage over classical digital simulations for the following cases. First, LBCMs with complex connectivity and moderately strong coupling strength to the bath, or models with dissipative bath modes and higher order coupling and anharmonicity. And these are pretty far-fetched goals. So in the meantime, we can play with several interesting small-scale models. Some are already done, but of course we can improve upon them. And so we hope that analog quantum simulations can ultimately open up access to models that more precisely capture the quantum nature of molecular systems. And yeah. So yeah, with that, I'd like to conclude. These are the list of the co-authors. Thank you again. And yeah, I would like to receive any questions. Thank you so much.
Thank you. Thank you very much. Can you hear me?
Yeah.
Clearly? I have two questions. First question is, if we want to go beyond the capability of the classical simulator, do we have any method for verifying or quantifying the analog calculations? Or how do you want to benchmark if you want to go beyond the capabilities of the classical simulator?
How do you go beyond classical simulations? I think
Yeah.
I lost the... So yeah, first is to identify a model that's classically intractable. I think that is actually a challenge as well. So yeah, this slide we're introducing the state-of-art classical digital calculations that required days of computation. However, they are still limited to about 1.25 lambda over delta, where lambda is the reorganization energy. So if we go, and also we had this, we observed this exponential increase in the runtime with respect to this ratio. So the idea was that if we, and also, and one more thing, the electronic sites coupling were all nearest neighbors. So for such a model, of course, rigorously analyzing the classical computation cost should be done, but yeah, this is what we suggest as a target. And if we identify this model, then this model can be straightforwardly simulated using trapped ions as I described. So using these basic operations. But of course, you need longer experiment time, so longer coherence time. Does that answer your question?
Yeah. And you mentioned that you kind of compare your analog quantum simulation with the state-of-the-art classical digital quantum simulator.
Yeah.
Are you also interested to compare with the digital quantum simulator versus analog quantum simulator?
Yeah, that's a very good question. We actually mentioned that briefly in the new revised version of our manuscript. I uploaded like 2 days ago. But in short, digital quantum computation typically requires a fault-tolerant quantum computer. So you have to do error correction and all that. So it's not something that you can run, especially if you're beyond the classically tractable regime. It's not something that you can run by like trapping like a few tens of ions on a single trap. You need like basically, I don't know, thousands, if not millions of qubits, probably millions of qubits to run a digital quantum algorithm beyond the capabilities of classical algorithms. So yeah, we want to see if analog quantum simulations can go beyond classical computation.
Further questions?
Sorry, can I ask a question?
Yeah,
do you have a systematic or quasi-systematic ways of estimating errors for the stuff which you cannot simulate classically?
So what we do in these plots to predict the performance of noisy trapped ion system is we literally solve the master equation, and the Lindblad operators are just those that represent these sources of noise, and you just evolve the trapped ion system's quantum state comprised of the qubits and the motional modes of the trapped ion chain. So of course that will work only for very small systems. So here, it's basic. Oh, I perhaps I didn't mention this is for n equals 2, so 2 modes. So you have 2 modes and single qubit. You can easily, not easily, it's still computationally heavy, but you can do these simulations. For larger models, you will not be able to run these simulations. So you probably will approximate the effects of these by some exponential decay or something, I guess. But that will be a very rough upper bound of your noise, effects of noise. So so if you have the characterization of these noise, like coherence time and heating rate, you can provide an upper bound, but it will be very rough, very overestimating your errors, I think.
Okay, thank you.
Yeah, thank you.
Thank you. Any other questions?
I
Go.
had a perhaps quite a generic question, so yeah, sorry, it's a bit broad. So most of your talk was focused on the simulation of many body systems, like the capacity of using trapped ion platforms in simulating open quantum systems. Because in the latter part of your talk, you referenced a paper, so I think it's the Lemma paper from 2018, which I think is a theoretical proposal of using trapped ion platforms for simulating structured, so a single two-level system that interacts with a structured path. I can't remember which slide it was that you referenced it, but it was towards the end.
Is this paper you're talking about?
Yeah, that paper, yeah.
Yeah.
So as far as I'm aware, that's a theoretical proposal for.
That's right.
Yeah. So do you know if much has been done experimentally, like how viable that is to?
Yeah, actually, yeah, it's a very good question. And actually, we are quite surprised that since this theoretical proposal, there has not been any experimental work following up. And this paper is also a theoretical proposal in a somewhat different direction, but basically the same method of laser cooling. I think the reason is because lasers are very expensive. And yeah, I work with the trapped ion experimentalist, and cold trapping different species of ions and having lasers that can do coherent operations on this and like cooling on this. Lasers are very expensive, so you need a lot of lasers, and I think that's the reason, really. And also probably because setting the parameters for laser cooling could be hard, like controlling the cooling rate or the binary population could be hard. Of course, there are a lot of experimental challenges, but I also kind of find it surprising that the experimental work has not been done in this direction yet. There, of course, I know a lot that looking for this direction, but there's no like really. I don't think they're close. So yeah.
Yeah. I mean, I'm not an experimentalist. I don't know how hard things are to do experimentally, but yeah.
Yeah, it's just pretty hard. Not only because the complexity, but also because of the price, I think, of the lasers. That's what I heard. Yeah.
Thank you.
Yeah, it is a problem, but obviously not the only problem. And what our experience with the trap is that you have so many systems that you have to keep working optimally because it's the lasers, it's the frequencies, other microwave and yeah. But it's lovely that the theory can be done first.
Yeah, but I'm pretty optimistic that this will be done sometime soon.
Will be done sometime, yeah.
Yeah, you should consider doing it if you, yeah.
Excellent. Are there a few other questions? No. Then, Mingyu, thank you so much for your time, for giving us a very nice, very exciting simulation techniques, and keep us in the loop of what you do, so that maybe in the future we can invite you again. And
yeah, please reach out to my email if you have any questions. It's just my name, ready to use. So
perfect. Thank you very much. Thank you, and have a good rest of the day and a nice weekend. Yeah.
Yeah. Thanks for inviting.
Have
a nice weekend. Thank you all.